Well, I'd like to thank all the organizers for the talk, for having me, as well as Cassie and all of the speakers before me for setting up a great sort of context. I got to delete 2 of the slides that I was originally going to show you. Sorry, beautiful photo from the 2017 talk. But yes, so I'm going to be talking about a paper that was published earlier this year in May, talking about the circumgalactic metal content in the context of the M-sigma relationship. And I'm particularly interested in the impact of AGN feedback on the stellar regulation of Milky Way mass galaxies. And so I do that using SPH simulations of Milky Way mass galaxies. And I did a comparison from some simulations back in 2019, comparing to the Cost Halo survey, which I'm sure we all know and love, looking at the column density of O6, and I'm going to show you the final result of that paper, and if you want to know more about it, we can talk about it later, but it is the motivation for the work that I'm going to talk about today. And so here we have the column densities of O6, right? We're looking at the hot phase of gas in the CGM. And what I have just added to this plot are column densities from 4 Milky Way mass galaxies run with the Changa code. It's an SPH n-body code. I'll talk a little bit more about the details of that code in just a minute. But I ran 4 galaxies with and without the black hole physics that we include in our simulations, and you can see the results of that here. The solid lines are the galaxies with black hole physics, the dotted lines are those without black hole physics, and you can see this discrepancy in the amount of O6 in the CGM of galaxies without black holes. And so the critical result of this paper was that in our simulations, the supermassive black hole was responsible for enriching the CGM of these galaxies by evacuating the metals from the disk where they were forming and moving them out into the CGM. And so the paper that I'm going to discuss for the rest of this talk is answering the question, if the supermassive black hole is moving these metals out of the disk and into the CGM, where do they then go? Do they stay in the CGM? Are they evacuated out into the IGM? And how much is left within the disk? And to do this work, I've been using galaxies from the Romulus 25 simulation, which you can see running in temperature here. This is Romulus 25 with a 25 megaparsec cosmological volume with about 1,000 galaxies from 10 to the 8 to 10 to the 13 in solar mass for their halo mass. This includes, it adopts star formation, stellar feedback, UV background radiation from the gasoline simulations, and we have an improved subgrid mechanism for black holes. So we see black holes in a physically motivated way from direct collapse. We have a consistent and physically motivated dynamical friction prescription, which allows our black holes to settle naturally at the centers of galaxies rather than being pinned there, and it naturally produces large-scale outflows. So from the Romulus 25 simulation, I selected 140 galaxies between 3 times 10 to the 9 and 3 times 10 to the 11 solar masses, so matching the mass range of Cos halos, as well as splitting the sample into a star-forming and a quenched sample or passive sample using the same specific star formation rate cut as Cos halos. And you can see them here on the M-sigma relationship. We're going to come back to this plot sort of again and again as I relate the metal content of these galaxies to the M-sigma relationship. And so to answer this question of where are the metals in these galaxies as a function of what is going on with the supermassive black hole, I have a quantity on both of these axes that I'm going to call the metal retention fraction. And so for the CGM, that is the total metals present in the CGM at redshift 0 divided by the total metals produced throughout the run of the simulation within that halo, all of the metals produced by all of the stars throughout the evolution of that galaxy. And similarly, that same calculation, but for the metals present in the disk on the x-axis. And so what you can sort of to be more clear about how you can interpret this plot, if we take one sort of red point here, this galaxy has 55% of all of the total metals formed in that galaxy in the disk, see along the x-axis, with 15% of them remaining in the CGM. And this distance between this gray or darker line and any points below that is the fraction of metals lost to the IGN. Whereas a galaxy like this blue one I've highlighted here on this gray line has maintained all of the metals that were formed either within the disk, in this case 90%, or 10% of those metals left in the CGM, but it hasn't lost any to the IGN. And so the critical things to take away from this plot are we have some galaxies, the star-forming galaxies, that are maintaining most of their metals in the CGM, right? They're not falling very low below this gray line, while nearly half of the quenched galaxies can lose up to 50% of their metals. These circular points are losing much more of their metals to the IGN. But I want to highlight the color bar here, this quantity delta MBH. This is the deviation from the empirical M sigma relationship from Cormindy and Ho here. So this vertical distance from this line to each point is this delta MBH. And we're going to consider that the overmassiveness or undermassiveness of a black hole relative to their stellar dispersion, or as a proxy relative to the gravitational potential well in which they live. And so the other thing that you can take away from this plot is that the majority of the galaxies that contain undermassive black holes for their respective gravitational well are maintaining, in the blue regime down here at the corner, are maintaining most, if not all, of the metals in their galaxies, and primarily within their disk, whereas galaxies that contain an overmassive black hole are evacuating more of their metals to the IGM and have more of their metals out in the CGM as well. And so here I'm now plotting this metal retention quantity as a function of delta MBH, which I just described to you. And the key thing to take away here is this additional information of the color bar, which is the fraction of total disk metals in the stars. So in the previous plot and in this plot, I've shown you where those metals are. Right? There's primarily they're being maintained in the galaxies with undermassive black holes, and they're being more evacuated in galaxies with overmassive black holes. But within those two subpopulations, the galaxies that have undermassive black holes, the metals are locked in the stars of those, in the central region of those galaxies. Whereas in the overmassive case, the metals are still in the gas phase in their centers. And so what we end up having is these two populations which appear to be having these different sort of evolutionary cycles and different characteristics. We have galaxies with undermassive black holes that have higher mass and more metals in their centers for their stellar populations, right? Those metals are being locked in stars. And then the galaxies with overmassive black holes in the red have less gas and less metals in their centers, and more of those metals remain in the gas phase. And so we have these two sort of evolutionary populations where galaxies with overmassive black holes living in shallower potential wells are more effective at evacuating metals from the disk into the CGM, but in our simulations, not far out into the IGM. And you have more stellar regulation where the disk metals are being maintained in the gas phase. And on the other side, you have the undermassive black holes living in galaxies with steeper potential wells. More metals are being maintained in the disk, and those metals are being locked in stars, and you see stellar regulations as a buildup of stars locks those metals in place. And so the key result from this work is that the scatter in M sigma may be indicative of how effective a supermassive black hole is at ejecting metals from its disk, or sort of more concisely, the scatter might matter in the evolutionary lives of these galaxies. And this may be potentially observable in future observations, right? We care about a bunch of different phases in the CGM. So looking at observations of disk metal retention might show this. We've already ruled out C4 measurements, looking at column densities in C4, which is consistent with recent results from the COS HALO survey from Garza et al. 2024. However, potentially this might be observable in hotter gas, looking at high ions in the UV, or more recently, some upcoming work that I have in the X-ray. Thank you so much for your attention. I will now take questions.
Very interesting. So In addition to the black hole mass, there's also black hole activity, like accretion to the black hole. So have you tried to fix the mass of black hole, whatever it is, and increase the accretion to it from like a sub-Eddington to super Eddington, and just try to see how much the injection of materials like metals to IgM may be affected? Because you could imagine you have very massive black holes, which is almost quiet.
Yes, so I think that that's really interesting. That's not something that we've done because all of these galaxies were selected from a cosmological volume, and so tweaking those parameters is not something that we had access to. But it would be interesting to see how different feedback mechanisms and, in addition, different accretion could impact these numbers. Absolutely.
Nice talk, Nicole. The black hole mass and the CGM metal mass are both cumulative, right? So as one, they should go up together in your scenario. But the fact that there is such a correlation suggests that there's not a lot of metal ejection occurring just from star formation when the AGN is on, or it would tend to erase the simulators.
Yes, exactly.
Is that consistent with what you find, or?
Yes, absolutely. And I think there's some interesting work being done by a graduate student at the University of Washington, Oge Okoronkwo, who is working with Jeff's work. And she is looking at the metal time, or the gas time scale and the recycling time scales in simulations like this, because that is a really interesting question. I didn't talk too much about this paper, but another result from this paper from 2019 was that these 4 simulations here with the solid lines, ignore the no black hole runs, have different star formation rates, and a couple of the red ones are actually quenched by redshift of 1 and don't form stars for the rest of their lives. So that tells us that at the very least the setting of some of the hot gas, at least traced by the O6, is being set earlier for sure.
Any more questions? Let's thank the speaker again.